Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at some past year A-level questions which test on this topic of the theories of acids and bases from the JCH2 chemistry syllabus. So as a recap, these are the three learning outcomes of this topic. Basically, to summarize, is to be able to state the Arrhenius definition of acids and bases, the Bronsted-Lowry definition of acids and bases, including the concept of conjugate acids and conjugate bases, as well as to be able to state and apply the Lewis definition of acids and bases. So the first question that we have, November 2014, paper 1, question 32. Which statements about the ammonia molecule and the ammonium ion are correct? So let's just talk about this first. So the ammonia molecule is NH3 and it has a lone pair of electrons. So it can accept a proton to form the NH4 plus cation. So in this case, this will be a base because it accepts a proton to form the NH4 plus. Okay, when it forms the NH4 plus is now the conjugate acid because it can donate a H plus cation and return the NH4 plus back to the NH3 base. So this is really the conjugate acid of the base ammonia. So it is true that the ammonia molecule and the ammonium ion are a conjugate acid and base pair. So one is true. They contain the same number of electrons. So the total number of electrons of the proton is 0. So obviously the number of electrons of this, whatever the number is, plus 0 electrons will be the exact same number of electrons. It will arrive at the same number of electrons. So this definitely will have the same number of electrons as the ammonia because you're adding 0 electrons to get this. So they contain the same number of electrons. This is also true. They can both act as ligands in a complex ion. So in order to discuss this, I kind of need to give you a brief overview of transition metals or basically metals in general. So for example, if you have a Fe2 plus cation in solution, right? Because it's surrounded by water molecules and water actually has a lone pair of electrons on the oxygen. So what can happen is that the oxygen can actually use one of its lone pair to form a dative covalent bond with the Fe2 plus. Okay, and like in actual fact, there will actually be 6 water molecules that forms dative covalent bond in solution when there is a Fe2 plus cation in solution. Okay, so although I draw it like this, right, but it should be noted that all these are all dative covalent bonds. And the thing about this is that when the water molecule or any substance that uses its lone pair of electrons to form a dative covalent bond with the central metal cation, all these substances will be known as ligands, and this will be revisited and retaught in the chapter of transition elements. So the ammonia molecule and the ammonium ion, can they both act as ligands in a complex ion? So basically, as I've mentioned, ligands are substances which have a lone pair of electrons that can form a dative covalent bond with the central metal cation. The ammonia actually has a lone pair of electrons, so you can form a dative covalent bond with a central metal cation such as iron 2+. However, the ammonium cation, right, because the lone pair has already been donated to a proton, so there is actually no lone pair of electrons around this nitrogen that is available for forming a dative covalent bond. So this one has no lone pair of electrons to form dative covalent bond to a metal ion. So since it doesn't have a lone pair to form a dative covalent bond to a metal ion, the NH4 plus will not be able to act as a ligand in a complex ion, while NH3 is able to. So this is not true because only the ammonia, as mentioned, can act as a ligand. So since 1 and 2 is correct and 3 is wrong, the answer will be B. Only 1 and 2 is correct. Okay, so this question, November 2013, paper 3, question 2A and 2B. So explain what is meant by the terms Bronsted-Lowry base. So basically a Bronsted-Lowry base is a proton acceptor. And the conjugate acid base pair, the way they'll explain this is the following. So I'll write out this equation. So HA becomes H plus A minus, and this will be the acid because it basically is a proton donor, and this will be the conjugate base because the base originated from the HA when it lost a proton, and it is a base because it's able to accept a proton to go back to the original acid. So this HA and this A minus and this A minus are conjugate acid-base pair. So if I were to answer, I'll write out this equation and then explain it as and I'll write the explanation that I've given. Okay, so for part B, the ammonia molecule can react in various ways as an acid. Okay, so let's be clear what it can be first: as an acid, as a base, as a nucleophile, as an oxidizing agent, and as a reducing agent. Okay, so here I would like to point out a few things first. So for a base, right, and a nucleophile, to be honest, if you were to talk about base in terms of the Lewis definition, Lewis bases are electron pair donors. And as we have mentioned in the previous lecture, nucleophiles are also electron pair donors. So to be honest, if you say that something is a Lewis base, it is necessarily also a nucleophile. But in this aspect, we would like to talk about the acid as a Bronsted-Lowry acid, the base as a Bronsted-Lowry base, while a nucleophile is using the Lewis definition. Okay, so let's just be clear on that. Because if we were to use the Lewis definition, a base will also be a nucleophile. So it doesn't make sense to be give an answer as either a base or a nucleophile because it would overlap. Okay, so for the purpose of this question, we would treat the acid and the base by Bronsted-Lowry theory and the nucleophile based on the Lewis theory. For oxidizing agent and reducing agent, we haven't really gone through electrochemistry and redox improper. So I'll just give the answer, and those of you that can follow can just follow first. And those of you that cannot, perhaps you could later when we visit and I teach electrochemistry, you can come back and see whether you get this question or not. Okay, so study the following reactions and decide in which way ammonia is reacting in each case and explain your answers fully. So for this first one, right, ammonia dissolves in water to form NH4 plus and OH minus. Okay, so this is actually NH4 plus and OH minus. And since it dissolves in solution to form OH minus, by the Arrhenius theory of base, the NH3 is acting as a base in this case. Okay, if you go by the Bronsted-Lowry theory, the NH3 actually accepts a proton from water. So it's a proton acceptor, so it is also a base. Okay, so whether you use the Arrhenius theory or the Bronsted-Lowry theory, you will still arrive at the answer that NH3 is a base in reaction 1. In reaction 2, you look at the oxidation state of nitrogen, it will actually be -3, okay, because of the fact that the oxidation state of one of the hydrogen is +1, so there's 3 of them, so this will be +3. And since this thing is neutral, the oxidation state of nitrogen has to be -3. The oxidation state of nitrogen in this case is 0, because it's in the elemental state. So as the oxidation state changes from -3 to 0, it actually increases. So the nitrogen is actually oxidized. Okay, and since the nitrogen is oxidized, this will be a reducing agent. Okay, as I've mentioned, we haven't covered redox properly, improper. So if you are not familiar with what I'm saying here, you can revisit this after we go through electrochemistry. Okay, for this case, what we need to understand is that this is actually Na plus and NH2 minus. Okay, so what happens is really that the NH3 actually dissociates to form NH2 minus and H plus, whereas for this NaH, right, it actually dissociates. Okay, let me write it here. NaH dissociates to form Na plus and H minus. So what really happens is the H plus reacts with this H minus, okay, here, to give you the H2 gas. Okay, so in this case, if we look at the ammonia, it actually dissociates to form a H plus, so it's actually a proton donor. So based on the Bronsted-Lowry theory, we can say the NH3 here is a acid, okay, because it's a proton donor. Okay, so that's for reaction 3. For reaction 4, if we look at the oxidation state of nitrogen here, it's -3, again, for the same reasons as reaction 2. And if we were to look at the oxidation state of nitrogen in N2H4, so the oxidation state of hydrogen of one of them is +1, since there's 4 of them, the total of +4. And hence the oxidation state of one of the nitrogen must be -2, right? Because -2 times 2 will be -4. And if we were to add 4 to it, we'll get 0, which is the charge of the entire molecule. And since, again, the oxidation state increases from -3 to -2, N is actually oxidized. And since the N is oxidized, the ammonia in reaction 4 will also be a reducing agent. Okay, finally for reaction 5, right? This is a classic nucleophilic substitution reaction that you will learn in organic chemistry. So let me just elaborate a bit for the moment. So I'll just look at this COCl molecule. So the COCl molecule looks like this, and because of the fact that this carbon, right, is attached to electronegative elements in the form of oxygen and chlorine, so the shared pair of electrons will be closer towards oxygen for these two pairs, and the shared pair of electrons between C and Cl will be closer towards Cl. And as such, right, the carbon will acquire a partial positive charge, and the chlorine will and the oxygen will acquire partial negative charges. So what happens is that because the NH3 has a lone pair of electrons, and the lone pair of electrons is being negatively charged, will be attracted to this partial positively charged carbon. So it will actually attack this carbon and it will kick out this chlorine. Okay, and in doing so, basically this ammonia is acting as a Lewis base because it's using its lone pair of electrons being donated to this carbon, and this is actually acting as a Lewis acid. Okay, so of course, if it's a Lewis base, then we would say that in this case, the NH3 is a nucleophile. Okay, it's very like I said, nucleophile are Lewis bases, but most of the time when we use talk in the domain of organic chemistry, we refer to Lewis bases as nucleophiles. Okay, so these are the 5 different types of roles that ammonia can play in different reactions. So that's the answer for this question. Okay, so those are the 2 questions, past year A-level questions that basically test on this topic. So with that, I hope you are now able to be able to answer these learning outcomes and to apply these learning outcomes to answering questions that are addressing this topic. So thank you for tuning in. If you like the video, just hit the like and subscribe button and stay tuned for another video by Einstein Academy. See you all again.